So, dear organizers, thank you so much for inviting me. Very sweet of you. I will give some kind of historical overview. Birdtracks, why Birdtracks? So as a starting point, I'll take a starting point that I had in front of me 15 years ago. There is a QCD diagram, and I wanted to compute its group theoretic weight. And I'll show, how a Tuft taught us how to compute it. And in the process, I want to say that by Birdtracks, we mean some kind of Feynman diagrams, but they'll be more precise than that. Or if you're thinking more in a group theoretical way, we're studying invariant tensors. Birdtracks are diagrammatic method of computation, which is diagrammatic from start to finish. As we get used to them, there are surprises, pleasant surprises. For example, you discover that negative dimensions make sense. And to me, most amazing at all, I can use this to classify all possible primitive invariants, and that gives me all semi-simple Lie algebras, which is very sweet. The story begins almost exactly 50 years ago. Gerhard de Tuft, in end of 1973, submitted an article in which he used the group theoretic structure of diagrams with UN symmetry, QCD diagrams, to show that if the diagram is planar, the group theoretic weight as a function of number of colors and is dominated by such diagrams, and he showed us how to compute it. So this was published in April 1974. So I'll take this as the birth of Birdtracks 50 years ago. And in personal terms, I read this paper and I asked myself, wow, that's nice. This is much easier than, weights in Weyl chambers of group theoretical representations. He did it for UN, but, I care about SUN, but maybe I care about SPN, or maybe I care about orthogonal symmetry, or maybe I care about E8. Can I do it? So to show how Birdtracks work as a computational method, I'll just work it out for this diagram that we started the discussion with. Suppose the symmetry is SUN. Then it turns out every time you see a gluon line, you can replace by a double line minus the trace. Every time you see a vertex, three gluon vertex, you can replace it by the trace of a 3-point electron loop or quark loop in two opposite directions. And by quark, we only mean defining representation. We don't mean quark. And the way computations in bird tracking work is, it's an algorithm. You place that guy here by a loop, then you use the identity of the projection operas whenever you see this. You can replace it by this minus the trace. And you do this systematically, and you get that a loop of 4 gluons in a gluon-gluon scattering diagram can be replaced by a loop over quarks in two possible directions, minus disconnected gluon diagrams And you substitute this into this diagram, the notice only has loops of length 4, nothing shorter. You just substitute, you get the answer. And there are even programs, there is software you can download. They'll do this for you, no matter how complicated your Feynman graph in quantum dynamics is. Its color factor you can compute by hand just from the pictures, and the only rule is that every time you see a quark loop, you replace it alone. It's a trace of identity number of colors, and you replace it by n square, whatever, and that's it. You're done. So that was what we learned from at Hooft 50 years ago. And, you know, maybe it's much older, but we learned it from him. And it's so much simpler than looking at explicit representations of SUN groups and weight diagrams and all kinds of crap we learned from official group theory. So my blackboard was full of drawings like that, ending in drawings like that. And I wanted to find a word that distinguished it from a Feynman diagram, saying that this is a diagram that in itself is entire computation. It's not mnemonic in which you substitute all kinds of stuff and you do the separate work. So my blackboards, and those days we had blackboards, was totally filled by such things. And my colleague, Bernice Durand, came into my office and she said, "What is this? This looks like a bird scurrying around a sandy beach." And I thought that was brilliant. Now, there is a mania in, it's a very human thing that, you know, everything has to be named after, let's say, Einstein, but not by Schmiegel, because nobody's ever heard of Schmiegel. So, you know, and I don't actually like it because I like the name to describe what a thing is. So much, you know, I'm thankful to Gelman for saying this is a quark and give the thing a name, rather than saying this is a Gelman, somebody's particle, like Klein-Gordon particle. So I liked it, but it's not pompous enough, and it, you know, one is embarrassed to say it. But thank you, Bernice. You were a good friend. Now, after a while, I published a paper on this, you know, a few years after I learned the starting thing from Gerhard at Hooft. And I discovered by looking at literature that Roger Penrose had similar drawings in his publications. So I sent him a preprint of my article, and a letter came back, and it turns out he was hurt because when I was 5 years old and not yet in a grade school, and my mother was too poor to have me in a kindergarten, so she just left me sitting in the apartment. Roger was only using this notation. And it's true. I'll show you a few examples. And then when I finally wrote a whole book about it, and maybe I'll explain why it requires writing a book. He said this was not Birdtracks. This was fornicating ostriches, and it's email from him. So I washed my hands from it. So aren't you happy you are at the Birdtracks meeting and not at the fornicating ostriches meeting? So Roger started this thing first. And when you look at this paper from the 70s, you know, published 2 years before my own, it's the stuff that we do. This has now happened, you know, for adjoint representation was it 2, so, this is 6 and this is 2, etc. You'll immediately recognize it. And what's beautiful when Roger Penrose does it, he has such a wonderful sense of aesthetics that just the pictures themselves are much more beautiful than, anything I draw. I mean, just look at this. Isn't it much prettier than what I just showed you a little while ago? So anyway, apparently for his PhD, doing Hodge something, he drew such pictures and they're very beautiful. Eventually, he wrote that book, which is, you should have that book. I have it by my bedside. See, it's right there. You should have that book. And it indeed has the things, it has these fornicating ostriches, which between us we call Birdtracks. So one thing that was very useful for me was, this notation where you use a dark bar to make things asymmetric and you cut it in two and they're called Cvitanović tensors. Very useful stuff, and I'm totally grateful for Viola, grateful for Roger. Now, chicken out from inviting to this meeting because, I watched him last Friday. It was a serious thing in quantum mechanics, meaning of this and that. So I feel like embarrassing that we draw him into drawing little pictures. But anyway, be thankful. So you could have said, why don't we call this Feynman diagrams? Well, I want to make a distinction. So Birdtracks are good in the same sense Feynman diagrams are good. You don't write all the stupid indices, letters, things like that. Now, Feynman diagrams are a mnemonic device. I draw a Feynman diagram, but then I have to spend like 3 weeks in my field theory course to teach people what a propagator is, what a vertex is, where are the I's and H's and all that. And then eventually how to rewrite this in parametric representation, etc. So this diagram has all topological information, but to do calculation, you have to encode it. And encoding is expensive. But for, what they call in this meeting Birdtracks, it's a calculation method. Not only you draw a diagram, but you manipulate the diagram without ever using any tensor index, etc., to do the entire calculation. You never, add anything else to it. So that's why I like to have a separate word. But if you want to call it, color strand diagrams, you're welcome. Or if you want to call it Einstein, Born, Penrose, I don't know, Sylvester graphs, be my guest. I hate all these stupid names. I mean, the rule is naming is that almost always when something has somebody's name, it was discovered by somebody else earlier anyhow, so what's the point? But Birdtrack means, what it says. It's an equation looks like Birdtracks and you just manipulate that. So one thing I like about this Birdtrack notation, things that look kind of a little bit obscure in long head notation are things like Wigner 3nj and 6nj control. In Birdtrack way of doing this, the completeness relation just says if I have 2 particles and 2 representation mu and u, if the symmetry is suburb of unitary group, to make it simple, then there is a completeness relation saying that this can be always written in terms of irreducible representation of this Kronecker product. This is the formula. It says, instead of having 2 lines, have some over intermediate state representation. These guys are called Clebsch-Gordon coefficients, but just 3 vertices. Even though Clebsch was a great mathematician, Gordon was a great why the hell do they have to have name on this? It's beyond me. And, this is dimension of representation, and this is normalization factor, and it's what it says. you take these vertices and contract them and sum them. And now if I have two particles interchange a third one, I can insert this relation twice. And I can again relate it to just one-dimensional thing times some weight. And that weight, you obtain by taking traces respect to L, because this is just the diagonal matrix. So it's this thing here divided by that, very pretty. And Wigner was the first one to discover it, but you're welcome to get it out of his beautiful book on quantum mechanics. The professionals hated it. It was Gruppenpest, and Slater wrote screeds against it while secretly using group theory in his calculations. But Wigner had this beautiful idea. It says any group theoretical calculation is expressed in terms of three numbers: a trace of the representation, that's called dimension, or the three vertex, two particles kind of squared, that's called 3J coefficient. And then there's this guy here, that's called 6J coefficient, and there's nothing else. So Wigner understood that everything can be expressed at what was called 3NJ coefficients. And, that's a Birdtracks picture for them, and that's Wigner's 6J symbol. And this leads us to the, early history of Birdtracks. So basically, there were two strands. One strand comes via Wigner, understanding that you can do group theoretic calculations using these 3NJ coefficients. I don't know whether Wigner ever drew a picture. I mean, actually, I've met him and knew him a little bit, but I never asked the question, so I don't know. But in 1956, Levinson, or Jutsis Levinson and Monegas in Estonia, I think, occupied by Russia at the time, explained, and wrote a book about how to do Wigner's theory in graphical form, and these are pictures like those ones, so they understood that. This is elegant way of doing everything. And then there's the lineage. So, chemists, atomical physicists like this stuff. Now, people who have a particle physics, quantum field theory background, they got inspired by Richard Feynman, who in 1949 made the first sketches, or maybe a little bit earlier, at Shelter meeting. And, he explained his calculation in terms of Feynman diagrams, which the old men, Bohr, Heisenberg, whoever, the old men were there, found totally disgusting, and they called it chicken wire, and they hated it, and they wouldn't take it. But they died eventually, and thanks largely to Dyson, we got used to Feynman diagrams to the point that we actually misunderstood physics in 70s, in particle heyday physics when new particles are being discovered. The natural language was the Feynman diagram, and they didn't understand path integrals and stuff like that, but there we are. So this lineage, presumably inspired Penrose in 52 or something. I don't know when he got to see first pictures of Feynman diagrams. He was in math and then general relativity, but I'm sure he saw them. And he's much closer to what we're discussing here, because he realized that you could extract, the symmetry structure of these processes, and that important things about were symmetrized and anti-symmetrized, what is called Young tableaus for a long time. But particle, physicists have to really learn stuff all the time. Then, for me personally, important date is 50 years ago, and I think it's true of the community at large. A graduate student, promising graduate student, there were 3 in my time at Hof, Georgia Parisi and Sasha Polyakov. We knew these were good graduate students. Anyway, he taught us how, avoid horrible things like Gell-Mann matrices of SU3 and DI, etc., and just replace them with pairs of lines. This is really great. And a few years later, I, in fit of Teutonic completeness, developed the way how to do it for all compact Lie groups. And I'll come back to it a little bit. But that's a very brief history. Of course, it's much longer if you dig backwards, but for today, this should do. And one thing I really like about the Birdtracks, or this diagrammatic way of understanding group theory and tensors, was the statement of invariance that comes for continuous group. And I'll come back to it. But, it just says, you can write it in terms of tensors with lots of notations, there is all this stuff here. But it just says that if you have an invariant tensor and you try to mess with it infinitesimally, messing with it infinitesimally means you nudge all of its external legs, there's all kinds of structure inside. You sum up all these small perturbations, and then invariance means that if thing is invariant under small perturbations, the effect is 0 in linear approximation, and that's a statement of invariance. So once you understand this as defining property of invariance, you immediately get Lie algebra because, a 3 vertex of quark antiquark gluon or something should be invariant. That rule should be same in Alpha Centauri and here and today and 50 years ago. So if you nudge the 3 external legs, you get a thing that's called Lie algebra. There can be a simpler way of deriving it, remembering if you have to go to a distant island. And among representations, there is a special one called, incredibly ugly word, but the one that obeys the symmetry of parameters of this transformation. It's called adjoint representation. Hate it. If you do that, that's called Jacobi relation. Great. So I'll come back to this because that'll be very important to us a little while ago. So now, once you get some hang of these diagrammatic ways of thinking, you sit in your office, you're a high-energy physicist, you've learned about, 3 quarks in antisymmetric combination form a hadron, and quark antiquark should be measured, blah, blah, blah. And now, let's say Bernice Durand comes into your office, or Tony Kennedy or somebody, and says, look, but what if on planet Z, you have quarks and antiquarks, but for baryons, you have a symmetric color combination because, you're putting 3 bosons together, there's some other thing. Is that possible? Is there a Lie group that allows for it from the algebra? Turns out, answering this might take 1-2 years or might take a lifetime. Not trivial. But thinking about it in this Birdtracks way turns out to be extremely powerful. Before this happened, B-particle physicists learned the stuff from Weil and other people, but basically killing Cartan. Killing was the guy who figured it all out. Cartan wrote it nicely a few years later, so it's called Killing Cartan. And it's ugly like hell. I mean, what you do in that thing is you take a very special basis for generator, which is raising, lowering operator basis in the center, so a particular basis. And then you show that on that basis, you get a lattice, and lattice has to be finite. And now you have to classify all these freaking lattices. And I spent 1 semester teaching an honest course in this stuff. And the problem is, once you're done, you get a complete list of all Lie algebras and to some extent Lie groups. For global properties, you need to know more. And you have no idea what the hell do these things mean. I mean, when they teach a rotation group, they say you have a length, and I am allowed to do anything to the length that doesn't change the length, right? And that's definition of orthogonal group. And if I don't allow inversion, then it's special. If I have a quantum amplitude and I take its magnitude square, then the group that doesn't change is called unitary group. So you understand what unitary group is. It's something that doesn't change the magnitude, the probability of your thing, but it changes phases. Fine. Symplectic group. Well, you've learned about Hamiltonian formulation of Newton's equation. So you know that there's symplectic invariance in them built, and it's more delicate, but you learn it in symplectic group. And then there are these other guys, very short lists called exceptional Lie groups, and it's little that people know about geometry. There are things called move-on planes, but basically have no idea what that graph is. You get to E8, it's 248 dimensional. Who the hell knows what this thing is? So being, a young person and impatient and not wanting, I mean, I taught the course in this graph, I didn't like it. Said, could we just forget killing Cartan and start from the scratch now that we know that we are supposed to take double line for unitary group? And indeed, there is Birdtracks tradition, in the English tradition. These people, because of Newton, were totally isolated from real mathematics, which all took place in France, Germany, Russia, etc., but not in England. But they were stuck on weird things like in theory of invariance. So here is, Sylvester's list of how you classify possible invariance. And to best of my ability, I said, I have no idea what it is. Let me just start from the scratch. But actually, this is where we start. We start in 19th century, and with the idea that Birdtracks say, I should just draw some pictures and they should have geometric meaning. So we know that if you look chord to antichord, we have unitary groups. But when you look at, length square, then we have either symmetric invariance, that's orthogonal, special orthogonal, or anti-symmetric, special, symplectic. And now, what happens if I have 3 things stuck together? So invariant tensors of order 3. They can be symmetric, anti-symmetric, and it turns out there's a very short list of interesting groups that have them. And the exceptional groups show up on this list. Then you take 4 of them, like, quadraquarks rather than pentaquarks or something. And it turns out one of the exceptional groups that's invariance for it. And that's about it. So I started ignoring totally carton killing following this. And now a remarkable thing happens. Remember, I wanted to compute this diagram. Maybe it contributes to the beta function in quantum chromodynamics or something. But the main feature of it, it has no loops shorter than 4. And following a tooth, I could do it for unitary groups, and generalizing the idea, I could do it for orthogonal symplectic. But now, suppose I only know that I have quadratic invariant, antisymmetric cubic invariant, and it satisfies Jacobi relation. Can I compute this thing for any group? Well, it turns out if you say there is no primitive invariant, meaning a dot with 4 lines coming into this, that's irreducible, I can do it. And you think of this, you think of this diagram as a matrix that takes, 2 gluons and sticks them into 2 other gluons. So it's kind of acts on a space of 2 gluon space. If you square this, do it twice, and you do this on the antisymmetric, symmetric subspace, etc. If you do it on antisymmetric subspace, then Lie algebra solves it. You end up with a quadratic equation. And that quadratic equation has 2 eigenvalues. And it turns out that these 2 eigenvalues, you can compute the coefficients, and they depend on the dimensional group, the capital N. And you look at this and you realize, I can rewrite this equation in a nicer way because I know that N should be an integer. And I can rewrite this equation as a condition of N in terms of eigenvalue parameter written here. So it says, what values of M can I have such that this combination is an integer, because dimension should be it. Now you got to work. Now the Birdtracks are really important. So this work was done commuting between Göteborg in Sweden and Copenhagen, where my partner was, abandoning me, but I had to commute. And it's done all by hand. And you find out that the irreducible representation in 2 gluon space, there are 3 of them, and one of them has explicit factor of 36 minus m. Now, dimension at this moment is not allowed to be negative, so it has to be either 0 or positive. So it turns out to find all possible solutions of this problem, what systems exist where 2 gluons multiplied adjoint representations are decomposed in irreducible representation. That's a rather short list. And here it is. And then you look at this list, and when you look at the highest possible value of M, you discover that all exceptional groups and all their representations can be arranged together. And they are all solutions of the same condition. And when you look at this, you realize, well, actually, I can extend this into a triangle. And out of Birdtracks and no place come all exceptionally groups, and they have a meaning because they have geometrical invariants that you interpret as volumes or antisymmetric things, the simple things, and that's a gift of Birdtracks, with which I do not know what to do. But this has all happened without Killing and Cartan. And the project is not finished. Other people have rediscovered this, like Doodling, 20 years later or so. Or, read the read the book or read the papers and understood them. And that's still in progress. Maybe it's called category theory. I do not know. I leave it at that. And you might well ask, the taxpayer was paying you to solve the problem of quark confinement. So why are you abusing taxpayer money and doing this stuff? This looks like bad mathematics. Well, I did it at night and on the ships and trains, so I did it on my own time. I think I didn't cheat anybody, I hope. But there is a more serious psychological reason. Why did I really get into this? And I'm doing this because, everybody's history of Birdtracks will be different, like Rashomon. So this is the history that I went through. In 1974, Teutcher, Knost, and I computed the electromagnetic moment to, let's say, 11 significant digits or 10 significant digits. And, we computed thousands of Feynman diagrams. And at that time, I felt that I was the only person who actually knew what's renormalization in quantum chromodynamics. And I'm still annoyed with nonsense I have to deal with from people who have only computed one diagram, so I have no clue what it is. But anyway, I was very self-assured and very happy with things we've done. They're pretty amazing. They broke the CERN computing budget and changed theoretical physics into a very expensive part, almost as expensive as experiments. But early spring 1975, I had to go. I mean, it's great. I was invited to Caltech. I gave a talk about work. And, I've gone other places, and every place else I could say, Knost and I did this, and it's 720 diagrams and 800 counterterms and this and ultraviolet infrared. And the answer is 0.92 times alpha over pi cube, where alpha over pi are units that Schwinger started computing magnetic moment in. His answer was 1/2 alpha over pi. It's on his grave. But, I had to do this in front of Feynman. I don't have much respect for most, men. I was raised by a single mother, so I don't have any respect. But for Feynman, I did have respect because I knew what's going to happen. He will ask me, okay, why is this sign plus and not minus? You had hundreds of diagrams and, hundreds or thousands of counterterms. Why is this number not 10 or 100 or any other number? This number looks like 1 to me in a first approximation. This must be the most precise agreement between theory, experiment, and all of physics, which it was at the time. But what does it mean? So, fearing, what will happen to me, I thought about it and I came up with a, Koch-Anarchist screen, whatever that word is, but maybe a crackpot thing. But, justified by many years, well, 3 years of handling. So, magnetic moment is measured in units. This is the Bohr value of the moment, and this little thing is called anomaly. And what one computes in quantum electrodynamics is anomaly, which is the magnetic form factor of electron correctly normalized. That's what the cell is. It's a wave function normalization. And, it's some formula, and you learn how to do it. And you end up with parametric integrals. They are maybe 13, 15 dimensional. And they have numerator which have 10,000 terms. I have no idea what else. But and each one has to be computed, and there are at least 720, and in practice many more. And you compute them, and you get numbers which are sort of random because they depend on what gauge you chose. So that's they just chose some coordinates, and that's not very helpful. And you add them up, and things happen. Now, Feynman went on records. I wasn't fearing for no reason. He wanted us to tell him, what's a good approximation to the first term of magnetic moment? And when you improve it, what's the second one? And, do we have any intuition about the size of this effect and the sign of this effect? So, when I did it, we did what's called A6 3-loop diagrams. Since then, we have gotten 2 more orders, 4 and 5-loop. And all the numbers, so Schwinger number is 1/2, that's exact. But the other numbers are, -3, +1, -2, and, who knows, +8 or something. Now, if they were just sum of random magnitudes of diagrams, there should be sum of square root of sum of squares. They should have a variance, and there should be 800 and not 8. So they're insanely small. And the signs seem to make sense. And this brings us back to, why I got into Birdtracks. The invariance statement for any invariant tensor is what's called in quantum field theory a word identity. It's a statement that, if you perturb photon and you perturb electron positron, the sum should be 0. It looks like a trivial identity for quantum electrodynamics, and it's a little bit fancier for quantum chromodynamics. So then, though it's not worded anyway, it has 17 other names attached to it. And what happens is that when you enforce this relation that your result is invariant, in other words, if I change my gauge, my prediction for electron moment should not change, because gauge shots are just a stupid way to break up the computation because you're not smart enough to do it any other way. And it turns out my calculation, these lots of diagrams, can be split up in very intuitive way into gauge invariant contributions, and they are counted. K is the number of photons that crosses external vertex in the 3-vertex diagram, electron moving in constant magnetic field. And M and M prime is photons that start and end on in leg or out leg, totally trivial thing. So each one of these numbers using this, one proves is invariant, gauge invariant. And now you look at values of gauge invariant sets, and what do you find? Schwinger has this number. Now, the rule is that you just count how many photons cross. If one crosses, then you get a minus sign, but if 2 crosses, you get a plus sign. And answer is around 1/2. The points are missing, and 1/2 either way is the correct sign. And we do this for 3 loop corrections. You get a bunch of gate set. All of them are either plus or minus 1/2. And at the time when I looked at this first time, I predicted that if this holds, roughly speaking, the answer should be 0 for 4-loop diagram. So this was a slightly wrong prediction. Since then, this has been done. And, typical sets. So 1 photon across, 3 photons on one leg, 1 photon across, 3 photons on one leg, 0 photons on the other leg. The answer is -2, roughly speaking. This guy is roughly 0. This is -1/2, and -1. Remember, Feynman wanted us to have a good, rough, approximate guess for the thing and then improve it. So this works. And what's the big deal? The number of gate sets is very small, and they're all supposed to be plus or minus 1/2. The number of vertex diagrams explodes by n double factorial. I mean, and let's say n factorial. And this is unreasonably small. It says each gate set is of size 1/2. And there's a little empirical rule, what a sign is that you are. And if you take my prediction seriously, you can sum up the series. It's just, power law, and you find out it's analytic. So the anomaly is analytic function, in this case, just polynomial, or rational polynomial of the fine structure constant. And why is that a big deal? Well, everybody who learns field theory is told that Dyson in 1952 showed that QED is an asymptotic series. Asymptotic series means that when you get to the nth order, the prefactor is roughly n to the n, or n combinatorial. My estimate just says it's n. It's a power. You can sum this up, right? It sums up in a pole. This, when you're lucky, you can do some Borel with summation, etc. This is hell. It's not good at all. So I claim, fear of Richard Feynman, that QED is actually finite if you correctly account for gauge invariance of your results. And I have a very naive guess, but if you can show that the gauge sound is bounded in any way, it's then my argument still goes through. It's an analytic theory. So this is what really my version of the history is, and it's not. We're not home. So I met my maker. He wanted me to know. I, invented in my personal way Birdtracks for real, for the all Lie groups, etc. Why? Because I could have huge number of diagrams I could resum, and they had the essential property that they split up a gauge invariant sets. So I was hoping that I would start from that way and rewrite quantum electrodynamics or quantum chromodynamics, not as an expansion in stupid Feynman diagrams whose number is factorial and they're hopeless, but as something that's finite, computable, and has a spirit that you understand every term and its correction to the term. So this was the homework for every bird tracker in 1974. And 50 years later, I haven't done the homework. And I'll leave it to the young people to do it. So this is called Meet Thy Maker, and it's 3 generations down from me. Sorry, the usual stuff. Yeah. And of course, you cannot hear anything because I forgot to activate the sound, and you're very lucky you cannot hear. So I will have to solve this problem. But thank you very much, and have wonderful 3 days of doing serious bird tracking after this silly introduction. So let's see. I should probably stop. Can I not stop recording?